il palco al prossimo speaker, l'ultimo speaker della giornata, quindi fate un mega applauso per Emanuele Fabbiani.
Grazie. We will see if this will be the reaction at the end of the talk. By the way, just to get started, a couple of disclaimers. The first one to the organizer and the MC. The last time I presented this talk, it ended up like this. And this was the stage of PyData Paris. And I ran a little bit out of time, and this guy was reminding me that my time was up. And the other disclaimer is to you. You told me that you're quite tired, and that's completely understandable. Yet, if you try a Google search for the topics we need to discuss today, this is one of the first results. God help us. And it's never a good beginning. However, I think that the topics we are going to discuss are definitely very important. Every time we use an LLM, it's like we're driving a car. When we drive a car, we do not know exactly how the thermodynamics of an internal combustion engine works. Every time we drive an electric car, we do not think about the Maxwell equations governing how an induction motor works. However, when the car breaks down, we need somebody to know these rules in order to fix it, or to at least to understand why it broke down. Let's make a couple of examples in the realm of large language models. This is a real conversation recorded by GPT-3.5. Some random guy was asking the model, what is the world record for crossing the English Channel on foot? And the model answered, according to the Guinness World Record, the fastest time for crossing the English Channel entirely on foot is 12 hours and 10 minutes. And the record was set by George Reef in 2016. Of course, there is no George Reef. Well, it might be, but he didn't set this record, because the English Channel is a 35-kilometer stretch of water separating France from England. And the only person that I know walked on water didn't do it for that long and chose a place that was much hotter than northern France or southern England. So this is clearly false, yet the model is very confident in giving us this answer. It's very well written, and it sounds plausible, it sounds credible. This is just a funny example, but there is something more dangerous. Probably many of you have read this paper. If you didn't, feel free to do it. This is the original paper presenting Codex. Codex was the first model behind GitHub Copilot. This was 2021. So Codex was a pretty small 18 billion parameters model derived from GPT-3, and it was inserted into the first public beta of GitHub Copilot. In this paper, the OpenAI researchers, all these guys with the 1 at the end of their name come from OpenAI. OpenAI researchers discussed about the limitations of their model. And I would like to read with you an extract of this paper. This is a quotation. You can find these exact words in the paper. Codex will generate code that is as similar as possible to its training distribution. That's what a large language model does. We will see it in a few minutes. If the user has some subtle mistakes in their code, Codex may deliberately suggest code that superficially appears good, but is incorrect. Why does this happen? Well, Codex was trained on Copilot, allegedly the whole of Copilot, even if the whole of public Copilot. There are many legal issues about that. And on the public GitHub Copilot, there is the code by Dan Abramov, and there is my code. Of course, there is a difference between the two code bases. The code by Dan Abramov, who's one of the core maintainers of React, is most likely very good, very well written, secure, without any major bugs or vulnerabilities. My code, well, is none of that, is pretty trash, pretty much similar trash. So now, put yourself in the shoes of the large language model. If you have a very nice, a very sound code base, the large language model will think, look, I'm in a code base like the one by Dan Abramov, and as my job is to suggest the most likely completion, not the best one, but the most likely, I will keep suggesting very good code. And I will not try to include some vulnerability in it or some major bugs, because there are none in such a code base. But if your code is similar to the code of a student or a young professional, well, think about that. What is the most likely completion? It is one that has bugs. It is one that has security vulnerabilities. It is one that it's not so reliable or easily maintainable. That's not a bug, that's a feature. That's how the large language model has been trained. But once you use that tool, you must be aware of that. Of course, there are methods to solve these issues. Nowadays, in 2021, there wasn't. But these are the motivations that push us towards studying large language model interpretability and explainability. I hope I have convinced you. Now I have 38 minutes to talk to you about how we can solve this issue. Before doing that, we need to spend some time discussing how does an LLM work. How is it trained? What does it happen when we click the send button in the ChatGPT interface and we check out the results? Well, a large language model is trained on 4 main steps. The first step, that is the longest one, it's the one that requires tens of thousands of GPUs, and it's the one that requires days, weeks, and even months of training, is pre-training. Pre-training means take all the text that you can put your hands on, legally, let's say, and mask some words, around 20% of the words. Now try to have your model fill in the gaps, fill in the blanks. This is how we teach children how to use the correct word. And this is exactly how we teach LLMs about our language, about the structure of our language. Very good. This is why we take the model from Meta and we fine-tune them instead of building our own models. This step is extremely intensive on data and compute power. Very good. After this step, we have a base model, a model that can understand the language and can complete text. Is it usable? Not really. This is something like GPT-3. If you have ever tried to use GPT-3, it was a very bad user experience because you had to start some text and have it completed. If you wanted to have GPT-3 build some code, you had to create a comment because usually the comment precedes the code. If you wanted it to complete a story, you had to write the incipit of the story, the beginning of the story. If you wanted it to write a sonnet like Dante, you had to write the first couple of verses like Dante. Good luck. Fortunately, the guys at OpenAI understood that this kind of model was bad UX and fixed it. They said, look, we can now take this model that knows how to complete text and have it complete a series of question and answers. We can take those question and answer from the wild, from Stack Overflow, from Reddit, from Quora, from other websites built like that, or we can pay people in order to answer questions and train the model on the dataset we generated like this. Now, this second step is the reason why Google paid $60 million to Reddit for their data. This second step may be the reason why Microsoft is trying to push you on LinkedIn to answer the expert questions, because this kind of data set is very, very valuable for training large language models. And this is cool, so you get a model that knows how to complete text, and you have it complete an answer from its very beginning. Nice. Then, this is pretty distracting. But it's cool. The third step now is trying to understand what is a good answer. How can you understand what is a good answer? Well, you have no choice. You must take people and have them evaluate answers generated by the model. How do they evaluate it? Well, either by expressing preferences or by giving marks. Things marks from 1 to 10, exactly as in school. Well, this can be done, this is done, but people have all sorts of negative sides. They get bored, they're inconsistent with each other, they want to get paid, which is pretty annoying if you're OpenAI. So what you want to do is to build a model that can replace people in this task. So you build a reward model. So now you have two models. One model that is the generative model that can answer questions because you train it so in step 2. And the second model that you call the reward model that can mark questions according to the preferences of real people. That's the reward model, and that's step 3. And now what you do is you put the generative model and the reward model to play against each other. So you have the generative model to create an answer for a specific question, and you have the reward model to rate that answer. And you update the weights, the parameters of the generative model in order to get the highest marks. This is reinforcement learning with human feedback. With human feedback, because every now and then, you still get people to mark questions in order to avoid the reward model to deviate from the preferences of real humans. And this is pretty much it. You get this recipe, you had the best talent, the best engineers in the world, millions, actually tens of millions of dollars, and you get a model like GPT-4. Nice. Now you want to use this model. And what a model like this does is just to predict the most likely next word. Actually, the most likely next token, which is part of a word, but that's a technical detail we're not going to discuss. So you have some text like a large language model is a computational model, blah, 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 and the model says other. And then this cycle repeats once again. So you take the text from a large language model to other, and you ask the model to predict the most likely next word, and is natural. And again, and again, and again, and so forth, and so on and so forth. Very good. Why can't these be easily explained? Well, I'll give you just one number, and it's 1.8 trillion. They are called large language model, and even the small language models have billions of parameters. And they're called as such for a reason. These models really work only if they are heavily over-parameterized, if they have lots of weights in order to approximate very complex functions, such as the ones that govern our language. So we have a complex problem, a very complex one. Now, what I would like to do in the next 30 minutes is to give you 3 shots, not a comprehensive discussion, because there is none at the moment. The answer to large language model interpretability is there is no complete framework to achieve large language model interpretability, but I can give you some ideas about research directions to achieve this goal and some results that were achieved earlier this year. We will comment here research results that are as recent as June 2024. Let's start with the first question. Which language do large language models think in? So, even now that I'm speaking in English, when I think about what I'm going to say, I'm thinking in Italian, because that's my mother tongue, and I'm more proficient in structuring ideas in my own language. Then I translate. How do large language models work? Let's see. Before doing that, however, I would like to give you a word of caution about lexicon. Here we use the word think because it's nice. It gives an idea of a nice picture there, but it's the wrong word. These models do not think. These models do not hallucinate. These models have no idea about what truth is, because nobody has told them what truth is. These models just compute the most likely next word, and they do it by multiplying matrices and tensor. Nothing more, nothing less. They achieve great results with this technology, but there is no humanification, no personification of just computation. It's just math and engineering, nothing more, nothing less. As useful and as impressive as it is. So what's the answer to this question? Yes. Large language models, at least the ones that we can study, because they were open sourced by Zach, think in English. Let's see why. This paper is a very interesting one. It came out this year from the research laboratory at EPFL Lausanne, research lab headed by Professor Robert West. And what they did was trying to understand how the large language model represent words inside them. So, just to be clear, an LLM is something like this, something of a lasagna of these different layers. The first layer is the one that receives your input, is a tokenizer. That is, it associates your string to a sequence of tokens. Tokens are just integer numbers that can be stored in a dictionary, and every substring is associated with one of these tokens. Then the tokens get projected inside a vector space of long, dense vectors. A vector is a sequence of real numbers by the embedder. So at the very beginning of its processing, what a large language model sees is just a sequence of vectors of real numbers. Again, nothing more, nothing less. You can try as hard as you want to have GPT-4 count the letters R in strawberry, but that's a very stupid problem, because what the model sees is not individual letters, it's just tokens that are projected into vectors. So actually, that's not a proof that the model is stupid or intelligent. Actually, it's really an ill-posed problem. It's just a way of understanding how the tokenizer works. It's just made that way. Very good. Then, these vectors that are internal representation of words or parts of words get processed by transformers. Transformers merge together the meaning of the words to create the meaning of sentences, paragraph, entire pieces of text, and to give some flavor to words that can mean the same thing in different contexts. Good. Usually, what you want to see from a large language model is just the output of the last transformer layer. Researchers from EPFL said, why should we? Why can't we take the output of each and every layer and see what the associated token is? So after the first layer of transformers, after the first layer of processing of words, what does the model think. So what is the internal representation of the model? And what they found is that there are basically 3 great steps in the processing of LLMs: an input step, an intermediate representation, and an output step. You can see them here in red, orange, and blue. So here in this slide, focus on the last column to your right. That is the output of a prompt that asks to translate the word flower in Chinese. So the 2 ideogram on the bottom means Chinese language, colon, and then there is blank. What you read in the last column is the output generated by the LLM at each layer. So on the vertical axis, there are the layers of the large language model for the prompt that ends with the blanks, right? So what you expect is the ideogram that translates flower into Chinese, and it's the correct one, the one that you see in the top right in blue. But what you can see is also that in layers 19 to 26, you have flower in English. And this is not a chance, this is a pattern. Here you have some charts that for different tasks represent the language of intermediate representations in Llama models. You can see that for every task, even for tasks that are just repeat this sentence in French, in Chinese, in German, in other languages, you have some layers where the internal representation of the word is actually in English. Sure, you can argue. These are models from the Llama 2 family that was trained on a dataset that was 89.4% made of English text. But still, these are multi-language models, so they can produce output and correct output in about 100 languages. So even though they can get input in every language and they can produce output in almost any language, these models always pass through the English one. So all the style, all the biases, all the terms that we use in English language, sooner or later will be used by these models for their internal processing. That's your first answer, and that's your first step towards interpret LLMs. Whatever you do, whatever the input or the output language are, you always pass through English, at least for these Llama 2 models. By the way, you have 6 charts here because the first row is for one task, translate this word into another language, and the second row is for another task, just repeat this sentence in a language that is different from English. You have 3 columns because these are the 3 sizes of the Llama 2 family, small, medium, and large. And now, we have our probably most interesting chapter. God help us, what is monosemanticity? As we know now that there is an internal representation of concepts in these large language models, an obvious question would be, okay, can we understand this internal representation? Can we understand what the model is thinking? I don't care just about the language. I want to know which concepts the model is processing when it reads some specific text or when it produces some specific output. Because the next question is, can I control it? Can I tell the model, look, multiply by 10 the effect of everything related to kindness. Multiply by 0.1 the effect of everything related to racism. Multiply by 0 the effect of everything related to terrorism. This would be an astonishing achievement, because as of now, the only ways we have to control the output of LLMs are either reinforcement learning with human feedback, that is something we do during training and it's not deterministic, or prompts. That is something that we do during inference, and again, not really deterministic. It turns out, at least experimentally, we can do both. This paper was published by Anthropic on the 31st of May 2024, so this is really the state of the art of research. After this paper was published, both OpenAI and DeepMind published their own research on the same path for their proprietary models. The guys from Anthropic took Claude free Sonnet, their state-of-the-art model at that time, and tried to use monosemanticity on that model. What the hell does monosemanticity mean? It means, let's try to transform the internal representation into a vector of 0 to 1 flags. Each and every flag is associated to only one mono, meaning semanticity. So I have a vector of values going from 0 to 1, where each value represents one semantic idea, one thing in the real or the abstract world. So I have one item for that vector that represents kindness, one that represents racism, one that represents bugs in software, one that represents the Golden Gate Bridge. How can you do that? Well, you do it by using an autoencoder on the intermediate representation. An autoencoder is just a module of deep learning that takes a representation, a vector, projects it into another space. So imagine the vector that represents a word. You project it into another space where you only have 0 and 1s, and you try and recreate the original input in order to train the autoencoder. So it's a way of compressing information, if you want, and you train it to recover as much information as possible from your compressed representation. In this case, the compressed representation activates just a few of these flags, not all of them, just a few. And you do this by adding an L1 penalty to your training loss function. Good. How does this work? Well, this is a representation of the activation of the flag that is associated to the Golden Gate Bridge. You see, the more orange the text is highlighted, the more the value of this feature is close to 1 for that specific token or for that specific word. We see that it works. This flag activates when we are talking about the Golden Gate Bridge. And the same for brain sciences. This flag activates when we are talking about neuroscience or brain or surgery or something like this. And you say, good. Is this useful? Yes, it is. Because you can also use it to control the model. You can reverse engineer which parameters led to that flag firing, and you can either max out or diminish their influence. So you can build a variant of Claude 3 Sonnet, a variant of an LLM that thinks only about the Golden Gate Bridge. You do 10x the weights associated to the Golden Gate Bridge, to that specific flag, and you get what I'm showing here in the slide. A model that thinks it's the Golden Gate Bridge. You ask it to create a love story, and it's set on the Golden Gate Bridge. You ask it to create a zombie apocalypse, and it's set on the Golden Gate Bridge, and so on and so forth. And you would argue, that's a game. Is it any useful? Probably not for the Golden Gate Bridge. But what if the thing that you want to max out is gender bias awareness? You get a model that is extremely sensitive to any gender bias issue. And what if you zero out the weights associated to terrorism or to the creation of weapons? You get a model that is safe by design, not because of some guardrail that may work or may not work, but because its very weights are forced to behave as we want. I want to be very clear, this is experimental. There is no version of this that is publicly available, not from Anthropic, not from OpenAI, not from DeepMind. Will this be the way we will finally manage to deterministically control large language models? I have no idea, nobody has, but it's a very nice direction. Last topic I want to cover, do large language models memorize? Do they have the ability to repeat exactly some sequence of text they have looked at in the training set? And here the answer is, unfortunately, yes. And it can be mathematically proven that this is not only possible, but this is necessary for them to work very well. And this is weird, and this is problematic, and I will explain in a few minutes why. This is, again, a paper. If you want to go deeper into this topic, I strongly suggest you read it. It was published in November 28th, 2023. So again, this is the, I think, the least recent paper we are going to discuss today, and it's like less than 1 year old. This paper brought to the attention of the public an issue that you may have heard of. What about this? Did you heard about the jailbreak of OpenAI, of GPT-4, when you could ask the model to repeat the word poem forever, and what you got after a while was personal information of real people? This happened. OpenAI was really pissed off when this came out, and what they did was to put a guardrail saying, look, you cannot ask our model to repeat a word forever. This is a violation of terms of services. Of course, this is not a solution of the issue. This is just a workaround. But why does this happen? Why does a large language model repeat a word for a while and then spits out personal information of real people? This was, I mean, this guy, the guys from this paper actually phoned this phone number and someone answered, which is pretty weird, and also pretty worrying. Well, the point is that this happens not only about text with large language model, but it also happens with pictures in diffusion models like DALL-E, Midjourney, and so on. So you can see on the on your left a picture in the training set associated with a specific name, which is pretty uncommon, and Graham Lotz, I think. And if you ask the model to generate a picture with the name as the prompt, it generates exactly the same picture. And this is a real woman. This woman exists. So why does this happen? Both large language models do this, diffusion models do this. They memorize some, and they seem like they memorize something that is unusual, which is pretty weird. This is a paper from 2019. Actually, this is the oldest paper that we're going to mention today, and it's also the last one, where a guy from Google Brain got together a very nice mathematical proof that deep learning models must memorize samples in order to get very low generalization error. And the samples they must memorize are the least common ones in the training set. So if you have a bunch of text that is very common, that looks all the same, there is no need to memorize it, because you can build something that is similar and you do not get penalized in your loss function, because, again, in the loss function, you fill the gaps. So if you fill the gaps with something that is reasonable, you don't get penalized a lot. But if you have something very peculiar, like a phone number that by definition is unique, or an email address that by definition is unique, or the pair of a picture of a specific person with their name that by definition are unique, at least if the name is pretty uncommon, then it's more efficient from a parameter utilization perspective to just memorize exactly that sample than to try and create something similar. So the rule of thumb is if you have very unusual samples in your data set, the model will rather memorize them exactly than learn to produce something similar. And this is very weird, but because very dangerous, because all personal information is, by definition, very rare samples. Actually, they should be unique or close to unique. Nice. But why does repeating the word poem forever trigger the regurgitation of this information? Well, think about the probability space where the model reasons. So you think about words like points in space. Personal information are, we have said, very rare samples, so they should live in a region of that probability space that is rarely visited. And how common is it to repeat a word forever in any language? Very uncommon, because it gives very few information, right? Nobody really repeats the same word forever. I mean, if I started 35 minutes ago to repeat the same word forever, this room would be empty, right? Because it's giving no information whatsoever. So it just so happens that the region of the probability space where long sequences of the same words live is the same where very unusual samples live. That is the region where the model memorizes. And this is why, if you ask the model to visit that specific region, it may happen that it jumps from repeating the same word forever to regurgitating personal information. And this is very hard to fix. This is one of the reasons why we should understand better how this model works. Because without a deep understanding, it is very hard to fix this issue. The best engineers in the world, the guys at OpenAI, had rather put a guardrail and claim an imaginary, honestly, violation of terms of services than try to fix this issue because they knew how hard it was. And this is it. I have told you no solution, but just some ideas of what we may have in the future. I'm Emanuele Fabbiani. I'm an AI engineer at Extreme.